Okay, so I start now.
To continue now, we have to Professor Anna Dubova introduce Professor Emmanuel Frenod. You can start, Professor Anna.
Okay, Professor, thank you very much for accepting the invitation to speak in our seminar. I will just say some words presenting you. So, Professor Emmanuel Frenod is a professor at Université de Bretagne Sud, University of the South Britain in France. He makes his research at the Laboratoire de Mathématiques de Bretagne Atlantique. His fields of research are asymptotic analysis, multi-scale numerical method for ordinary differential equations and partial differential equations, and tokamak physics. As a curiosity, I was wondering what is tokamak physics, and I discovered that it's acronyms that coming from Russia. So, yeah. Yes, it's mean that it is toroidal camera with magnetic coils. So it was surprising for me to discover that. So he's also a founder of the company CD, which sells scientific optimization, mathematical and all tools to as a company for the robust control of the activities. So today he will speak about two-scale Pic method as an alternative to Gyro-Kinetic Simulations. So thank you very much, and you can start.
Okay, so thank you very much for inviting me to give this talk. This is a joint work that is done with Sever Istroga, and it is a resuming of a work that I stopped, I would say, about 20 years ago. And so we start again this work relatively recently, and so I will explain what is known and what we did, knowing that what we did is just the beginning. So let's say that the motivation is to contribute to understand or to simulate what happens in a tokamak or a stellarator. So there are two devices in order to reproduce or to make fusion on the Earth in order to produce energy. So you see here some images that here is a stellarator and here is a tokamak. And the goal is to confine let's say plasmas made of hydrogen particles in order to make helium and to produce energy. And the confinement in those kind of device is done by strong magnetic field. Okay, so when you turn to let's say the framework in which we go when we want to make simulation of this kind of experiment, you use or you have to address what is called kinetic equation or Vlasov equation that are non-linear. And when you want to make simulation of this kind of equation, you use what is called Pic methods, so particle in cell methods, or semi-Lagrangian methods. And I will now explain the running or the functioning of that kind of method. So when you want to simulate a plasma, you have to consider this equation, which is df dt plus the velocity dot the gradient with respect to the position of f, and a fourth term dot the gradient with respect to the velocity of f, where f is a kind of particle distribution in position and velocity space. So in fact, here you have a 6-dimensional PDE to solve, and it is nonlinear because the force here depends on the distribution itself, because in fact a particle, the is submitted to an electric field, for instance, but will also produce an electric field. Okay, so when you want to simulate that kind of equation, or to calculate an approximate solution to this equation, the way to proceed with the Pic method consists in noticing that the solution of this equation is in some sense equivalent to the solution of this system. In fact, if you go further, you can see that if you consider that f, which is the case, is a function which is constant along the trajectories of this system, you write df dt taken in x and v equals to 0, and when you develop this, you obtain df dt plus dx dt gradient of x of f plus dv dt dot the gradient of v of f. And when you replace the expression of dx dt here by this expression and dv dt here by this expression, and when you say that this must be equals to 0 for every trajectory, you obtain this equation. So once you have remarked this, for solving this equation, you first, let's say, sample the function f over macro particles, so they are not physical particles, but statistical particles. So you make this sample. Then you push your particles according to this equation, the dynamical system. Then you obtain new position, and then you project again the new position and new velocity of your particles on a mesh in order to compute again the force field, and then you go on step by step like that. So you have at each step to calculate the force, push the particles according to this force, project these particles on the mesh, and recompute the field. Okay, so this is the way that we solve that we simulate the confinement experiment in tokamak or in stellar right. Okay, so now once we saw this, the other ingredient of the framework is that we have strong magnetic field. And strong magnetic field means that we consider or we have that B, the strong the magnetic field, is in fact something which can be written as 1 over epsilon B. So the force term, which is the Lorentz force, can be written as the electric field plus a magnetic force, which is 1 over epsilon V cross B. Okay, we consider that everything depends on epsilon, so I put epsilon everywhere. And then once I made this, I assume, or we assume, that B is given. Let's say that as in tokamak and stellarite, particles don't go that fast, you can neglect the propagation of the magnetic field. So you can just consider that B is given, and that E, this one, is given by the Poisson equation, which is divergence of E epsilon equals to the integration of F epsilon with respect to V, which is the density of charge. Of course, everywhere here, I forgot all the constant, all the physical constants. And what we want to do is to compute the Vazov-Poisson equation with a strong magnetic field. And it is well known that the trajectory of charged particle under a strong magnetic field is an helix, which follows at the first order the magnetic line, but not completely, except especially when there is an electric field or when B is not constant. So the thing that we have to do is to manage particles that oscillate, and if we want to make, let's say, effective numerical simulation, you have to choose a reasonable time step. So you have to remove, in some sense, the oscillation. And to remove the oscillation is in other words, to say that we want to build a model or an algorithm that generates directly the mean behavior of those particles. So I symbolically put it like that or that. But of course, we want that this behavior is conformal with what is the oscillating behavior. And potentially, we also would like to reconstruct, or to be able to reconstruct, this is an important part, the real trajectory, or a very good approximation of the real trajectory from the from the trajectory generated by the model, by the mean model. Okay. So, and the difficulty is always the same, is that the force, the Lorentz force, act on the particles, but the particles also contribute to the to the force, and so we need, for doing this removing the to remove the explicit presence of the oscillation in our model, we need to use a method like homogenization or two-scale convergence that are known to work on this kind of problem. Okay, so if I make let's say a summarize, we want to implement Pic method for Vlasov equation with strong magnetic field, and if you want to do this correctly, we need to remove, in some sense, the oscillation, keeping the right behavior of the model, of the solution of the model. Okay, so in order to do this, finally, I can, let's say, summarize the situation, saying that there are essentially two strategies, or two ways. We want to solve the Vlasov equation with strong magnetic field. One way consists in, and we want to remove the oscillation in some sense. One way consists in remove the oscillation directly on the Vlasov-Poisson equation with magnetic field, and then on the resulting model, on the resulting equation, you implement, or we apply the Pic method, and this is what I call in the following the Gyro-Kinetic Simulations, because the model that is used here is called the Gyro-Kinetic Approximation. The other strategy consists in directly implementing the Pic method on the Vlasov equation with strong magnetic field, and then making an asymptotic analysis to compute the oscillating trajectories that are involved in this Pic method. And this is what I will call in the following the two-scale Pic simulations. Okay, so we are here, and let's say that most of the code of the software codes that are used in the industry use this way. And what I see is that it is certainly possible to proceed this way, and this is what we are trying to implement for the time being. Okay, so I will start to explain this way, and then I will explain this way, and I will, for both, explain, let's say, the advantages and the drawbacks, and to see what is. I don't say that there is one better than the other. Both have advantages and drawbacks. Okay, so this way consists in first making an asymptotic analysis in order to simplify or to remove, in some sense, the oscillation that we have in this model. And for this, so there exists, and this is a result which is known for years, that we can build a change of coordinate that will transform xv into z, gamma, and j, that will depend on something that I will call an order, which is such that your Vlasov equation with oscillating, with strong magnetic field can be rewritten as this new kinetic equation, nonlinear kinetic equation, with which reads d epsilon dt plus a term here or a factor here that does not depend on this component gamma up to another O into epsilon, then you have something which is 0 up to another O minus 1 time dj dj, and then you have lastly something which is which describes the dynamics with respect to this variable gamma. Okay, so this result is known but not well understood clearly, and this is what I will try to explain now. Because what is the way to build this change of coordinate? And let's say that if you look this thing at a coarse scale, without going into the detail, you can say that gamma is nothing but an angle in a system of in a cylindrical coordinate system, and J is nothing but a magnetic moment in this kind of coordinate system. But in fact, the reality is not exactly that. The reality is that it is almost this and not precisely this. So before explaining these drawbacks, I will explain how, once you have written your new system, how you can implement a Pic method. And so to implement a Pic method, the first thing you do consists in saying that, okay, you choose an order in order to have here something which is sufficiently small to neglect it, and here something which is sufficiently small to neglect it, okay? So maybe you can choose O being 2, 3, or so, or something like that. And once you have this, you obtain a much more simplified kinetic equation. Here it seems to not depend on epsilon, but in fact it depends on epsilon because there is also terms depending on epsilon that we neglect. So let's say that I do not really remove the epsilon, I just put it in gray. And then if you finally say, I'm not interested in the behavior with respect to gamma, then you say, okay, my solution does not depend to gamma, so dj epsilon d gamma is 0. And so you have, at the end of the day, a simplified equation, but in fact it is not only simplified, it is more a 4D kinetic equation and a 4D nonlinear kinetic equation. And in fact it is a collection of 4D kinetic equations which are parametrized by J. So in fact you reduce the dimension by 2 and you have a collection of a system to solve. Okay, so this is attractive because you reduce the dimensionality, you remove the oscillations, and you are you can say that you are happy. And essentially, this is used when for the codes that are implemented for simulation of tokamaks and stellar radar. But it seems that there is a kind of trouble, and that I will explain. So the way that you build your change of coordinate that will give you Z, gamma, and J from XV, in fact, is built using a succession of change of coordinates that involves a kind of Lie series, and I will go back to what is Lie series, which are parameterized by epsilon. So for each epsilon, you compute a Lie series. So a Lie series, what it is? A Lie series is a succession of small geometrical transformation in the 6D dimensional space. So small geometrical transformation means small in the sense of a geometrical transformation. So it is the transformation that are identity plus something small. in a sense of a transformation in geometry. And you have to make that kind of thing for each epsilon, because you know that the order in it, you're going to fix an order in epsilon. Okay. So when you say at the course vision that gamma is nothing but an angle and J is nothing but a magnetic moment, is in fact untrue, because it is almost this, but not really this. And as a consequence of all too small transformation, we have variables Z, gamma, and J that are not really easily interpretable, because they are the result of many the small transformation. So at the end of the day, you don't know exactly what to compute. This is what I think. And moreover, when you want to go relatively far in order, you have here really heavy expressions. Okay, but having heavy expression, this is an habit, or we are used to that kind of problem with this kind of physics. So this is not really the real problem. Okay, so this is the first way, and now I would like to explain the second way, which is the one that I propose to explore as an alternative one. Don't saying that it is better or worse, saying just it is an alternative possibility. So maybe we could go on this. And I tried to do this 20 years ago, and I will explain how to do. So we take the Vlasov equation with strong magnetic field. We write the Vlasov equation coupled with the Poisson equation, and then we generate particles, macro particles, sampling F epsilon. And then we write the dynamical system that those macro particles have to satisfy, and it is dx dt equals v epsilon, dv epsilon dt equals E plus V cross E3 plus 1 over epsilon V epsilon cross B, and you have, let's say, initial condition. So you have to compute the trajectory of an oscillating problem. So it seems to be reasonable. And let's say that when you do the asymptotic analysis, and I did it 20 years ago, finally, you know, you can clearly say that x epsilon, v epsilon is written as x0 taken in t minus n, something oscillating. These are the initial conditions, plus x1 plus x2, and the same for v. So you can make an asymptotic expansion that can be justified mathematically, and it is good, and it is a result which seems to be easy. And you can run a constructive method which is proven, which mathematical validity is proven, saying that here x0 v0 can be written as an oscillating reconstruction operator acting on a non-oscillating trajectory y0 u0, trajectory and velocity y0 and u0. So you can write that your solution initial is a reconstruction using an oscillating operator acting on to the non-oscillating trajectory, and you have the same result for x1 v1. You can say that it is an oscillating operator parametrized by y0 u0 acting on non-oscillating order 1 trajectory y1 and u1. Okay, so this is also attractive because you can also write explicitly the equation for y0 u0 y1 u1. But so you have something which seems to work very well, and what I think is that we are going to end by making it to work. But 20 years ago, I was not able to do it, and I will explain why. So you have a Pic method, you can make an asymptotic analysis on your particles, on your macro particles, and it seems to work. Okay, but the problem is the following: is that when you try to implement the computation with a b which is not constant, so let's say that you take b which is essentially not completely but almost tangent to a circle with a constant norm, and then you compute the thing. So you can write. So at the beginning, it is not that complicated. You see that x0 is y0, so no oscillation in fact. V0 is okay. A matrix which has, let's say, which is just a rotation matrix applied to U0, and then you can write a dynamical system with matrices that are, let's say, completely normal, and so there is no problem. So here at this level there is no problem. But when you go further, it begins to be harder, and when you try to write the thing for the order 1, you find that x1 has this expression in terms of y, in terms of let's say y0 parameter, in terms of y1, y01, okay, and parameterized by the order 0 trajectory. And when you express the equation for y11, you have this expression, which begins to be relatively hard. But when you go to V1, you have that expression for V11, for instance, and then the dynamical system for U11 is this one, and it is not finished. It is that one. So 20 years ago, I managed to do this using using Maple, and I stop here. And I think that essentially I was not able to make anything with this, and nobody else seems to be interested in making something from this. And recently, with Sever Histoire, we finally said, okay, let's consider that we can certainly, not using the Maple to calculate or to compute the right-hand side, which is complicated, but to generate a code by making a code generation. And then once we will have opened this scientific clock, which consists in saying, okay, I will generate a function, not a mathematical function, but a Fortran function or a C++ function or in any language function, in order to be able to incorporate it in any simulation, then it will be possible to run this equation. Once this scientific clock will be open, we will need to, of course, couple with the Poisson equation and then to embed it in a Pic software program. But for the time being, we have been concentrated on the scientific clock, and what we can see is that it works. And these are, let's say, results that are from yesterday, so they are very new. So here we have made the simulation, so it is the position of a macro particles. So it is just x epsilon of a particle in 3D. In black, we have the order 0 simulated trajectory, which is not reconstructed. And in red, we have the order 1 trajectory, which is reconstructed. So what we see, so maybe not super clear, but what we see is that when we compute the reconstructed trajectory at order 2, we have something which glue very well to the exact solution, or to the solution simulated directly. And in fact, if we look at the error, we have something which is in epsilon square. And okay, So, and the way to generate the code that makes this simulation is done using Maple, the code generation in Maple. So this is the position. So in blue, we have the position directly computed with the oscillating system. And in black, we have the order 0 not reconstructed, and in red, the order 1 reconstructed. Okay. So for the time being, we can say that the scientific lock seems to be now open. We are able to compute this. And here we have the velocity with respect to the first component. So we have the same thing, it works. And the velocity with respect to the second and the third component. Okay, so this works. And we are, I think that we are relatively exciting because it works. So I had no doubt that it was going to work, but I'm very happy to see that it effectively works. So we can reconstruct the trajectory with a much larger time step. That we can use a much larger time step to get the equation, the position from which we reconstruct the red point, than to compute the blue trajectory. Okay, so I also made the same simulation over. Sever who made this over a larger time duration, and okay, so we are happy. And the other good news for us is that finally the Maple code is not that big. Of course, you generate right-hand side, which is enormous, but in fact, you have a code a Maple code, which is relatively well made, and which writes over one page. And at the end, you put with code generation, and then you make a fortune from your right hand side computed by Maple, and then you have fortune function that you can put in your code to make your simulation. So okay, so now we can say that the scientific clock is open. So now we need to couple this with the Poisson equation. We are relatively confident to be able to do this because we have, let's say, a collection of results saying that the mean trajectory is enough to compute the Poisson equation. So, and then at INRIA Paris, where Sever works, we can access Pic software. So I think that now we are going to be able to finalize this work began, let's say, more than 20 years ago. Okay. To finish, I just want to give you, so here is the paper that I wrote in 2006, where I computed the asymptotic expansion of the trajectories. So it is asymptotic analysis. You also can read that book that I wrote over simplified transport equation. So the computation are not that complicated as here. And here is a paper that I wrote with Mathieu Lutz, where we have tried, and I think we have understood, or we described what we have understood from the way to build the geometric gyrokinetic approximation, which is not as simple as sometimes we can hear. Okay, so that's all that I wanted to tell you. So thank you very much.
Okay, thank you very much, Emmanuel, for this very nice talk. So let's ask to the audience if they have questions. So if you have any question, you can use the chat. Also, you can, yes, you can open your video and speak. So are there any questions? Johnny? Okay.
No.
I
No, no,
have.
no, no.
Sorry, Johnny.
No, go ahead. I don't have any specific question.
Just some curiosity, probably. So I saw that the solution you obtain with your method is not really periodic, no? So you expect it to have some periodical solution, as you see the reference solution has some periodicity, no? So
In fact, it is oscillating, but it's not periodic.
yeah. So
Okay. Because it follows the magnetic line, but not exactly. So you have drifts. So here we see a drift. So of course, when you are in a real magnetic field in a tokamak or in a stellarator, you have for the story. Tokamak comes from Russia, and stellarators come from America.
Okay.
Those are two technologies. Because okay, I think that in the 70s, Russians and Americans was thinking that they were able to make fusion on Earth for let's say a civil application in 5 years. But okay, it does not work because there is what is called turbulence, plasma turbulence, that makes that in fact you cannot keep the fusion long enough in order to produce more energy than the energy you need to make the confinement. Okay, this is the problem. But okay, but in fact we have many movements and so the trajectory is an helix, but following more or less, or following at the first order the magnetic line, but not really. There are drifts that depends on the on E cross B, on the magnetic variation, and so on and so on. There is all a zoology that is done about all those.
Okay. And what do you think about the classical numerical methods?
Classical numerical method, because the problem is 6-dimensional, and because you have a very oscillating things, very oscillating solution. If you don't make something before making the computation, you cannot compute over the time period that you need.
Something
so the goal is to
something accurate,
yes,
because of the oscillating behavior.
But what I think is that when you mean classical method, you mean by opposition to Pic method, or
yes.
Maybe you imagine just implementing, let's say, finite difference routine for doing this. Okay, I know that people try this, but it seems that because it is six-dimensional, it's very expensive to make this. And I think that people that try to make this on a reduced in 2D or 3D or in 2D positions, or for the position and velocity.
With some order reduction method, probably it can also work. Oh, I don't know. Just
certainly there are many strategies that are used, but what I know is that when you, for let's say effective real tokamak simulation than the one that are used with the people I discussed with at the CEA or at INIT for ITER. This is this kind of method that I use.
Okay. So thank you very much. Are there other questions or comments? So if not, we thank you again for being with us. Thank you very much.
You're welcome.
Thank you, Manuel. Thank you.
Thank you, Anna. Thank you a lot, Professor Emmanuel Frenod, for your amazing talk.